In this video, we explain how to solve a very interesting problem, consisting of determining whole hyperfaces of facets of cones and polytopes of any dimension. Consider, for example, a tetrahedron, which is a three-dimensional figure. It has four faces of dimension 2, 6 edges of dimension 1, and 4 vertices of 0 dimension. Note that edges are the intersections of faces and vertices are the intersections of edges. However, in a space with dimension 20, we will have hyperfaces with dimensions 19, 18, 17 to 1 and 0. Thinking in large dimensions and to avoid using different names as vertices, edges, faces, etc., we decide here to call off of them facets of dimensions n. So, faces here will be called facets of dimension 2, edges will be called facets of dimension 1, and vertices facets of dimension 0. Our aim is to identify all facets of any dimension of a given polytope. We remind the reader that the gamma algorithm, when obtaining the dual cone of a cone, in its last table provided the facets of maximum dimensions of the initial cone. Since we are interested in polytopes, we use a trick that consists of associating to any polytope a cone and see that the facets of a given dimension, say n in the cone, correspond to the facets of dimension n-1 in the polytope. With this, the gamma algorithm will also provide us the facets of any polytope. We explain all this with a simple example. Consider the pentagon in yellow color, which is a polytope in a two-dimensional space. If we add to its components one more of value 1, we get the cone in the figure, which is called the cone associated with that polytope. If you take a careful look to the figure, you can see that every edge of the cone of dimension 1 passes through a vertex of the polytope of dimension 0, so that the edges of the cone are associated with the vertices of the polytope. Similarly, the cone faces of dimension 2 correspond to the polytope edges of dimension 1. Consequently, facets of this cone and this polytope are associated, reducing dimension 1 unit when passing from the cone facets to the polytope facets. Thus, to find the polytope facet, what we will do is, first, we obtain the main facets of the cone using the gamma algorithm, and once we have these facets, by intersections of them, we will get the rest of the cone facets with smaller dimensions. Finally, to obtain the polytope facets, we use the above-mentioned correspondence, that is, from the cone n-dimensional facets, we obtain the associated polytope facets of dimension n-1. Next, we explain all this in detail with the example of a cube, which is a truncated cube by a plane cut that produces the triangular section in the figure. The parametric equations of the truncated cube can be written as A lambda as indicated, where the matrix A contains its vertices, and the Greek letter lambda refers to linear convex combinations. This means that the polytope can be generated by 10 three-dimensional vectors, its vertices. So, we build its associated cone, adding ones as the last new components, and get our polytope, which is defined on a space of dimension 4, while the polytope was initially in a space of dimension 3. To identify the main ETs, the largest dimension cone facets, we use the gamma algorithm to get the dual cone of this cone as follows. Since 10 vectors generate the cone, we have to use 10 steps, introducing the 10 generators one by one, which produce the initial plus 10 more tables. The last table gives us on one hand the dual cone, and on the other hand the main cone facets of dimension 3 in the lowest part of the table, which are also the truncated cube facets of dimension 2. In fact, in the first column below we have 1, 2, 5 and 6, which correspond to polytope vertices 1, 2, 5 and 6, that is, to the face behind the truncated cube. The next column is 1, 2, 3, 4, which is the face down. The third is 1, 4, 5, 7, corresponding to the face on the left. The following face is 2, 3, 6, 8, 10, corresponding to the face on the right and is a pentagon. The following is 5, 6, 7, 8, 9, corresponding to the top face, and the last 8, 9, 10, which corresponds to the triangle. All these look as magic and interesting. Using the algorithm without seeing what it represents geometrically, we discover what the faces are. Note that there are many other combinations of vertices which are not faces. For example, 5, 8, 10 or 5, 7, 2 are not faces. So it is wonderful to have an algorithm, the gamma algorithm, that identifies all of them. This may surprise us here in this three-dimensional case, but imagine a polytope or a cone in a space of dimension 20, and that we can discover the facets of dimensions 19, 18, 17, etc. This is exactly what the algorithm does. In the list above, you have the 7 facets of dimension 2 of the polytope, and if we want to get the facets of dimension 1, that is, the edges, all we have to do is to find the intersections of each one with each of the rest. If we take a moment to identify all intersections, that is, what common elements appear when we combine them all 2 by 2, we find all listed below. We can check that they effectively are all edges of the truncated cube. Incredibly, once again, we check that these are precisely all, absolutely all, and there is none that is missing, nor any missing edges, when there are many other combinations, couples, we are not edges. If we were in other higher dimensional space, for example 20, by successive intersections, we will obtain the hyperfaces of dimension 19, 18, etc., which is really interesting and surprising. I hope you have enjoyed this video where we have proved once again that the gamma algorithm goes a long way and allows us to solve very beautiful and difficult problems. Motivated by this experience, I invite you to the next video in which more interesting applications of this algorithm are given.